Greetings, AP Calculus BC students. Mr. Record here. Once again, we are dealing with e-learning day 2018 because of a nice snowstorm that's hitting central Indiana here on the 12th of January 2018. If you're watching this video, however, later on down the road, perhaps you're enjoying much better weather where you are. Anyway, I do hope indeed this video does help. We're sort of at the tail end of the unit at my school dealing with vectors and vector valued functions. And we're talking about some application problems that it's quite possible that students who do take advanced placement physics, the calculus-based AP physics, might end up having some kind of exposure to problems like this. And in the event, in order to be able to handle a problem such as example 8, you have to have some basic understanding about the structure of particle motion at an angle other than, say, along a straight line, and how vectors sort of merge into that. But there are several other videos that you can find online about solving motion problems with vectors that might be helpful prerequisites for this particular problem. But in any event, this problem is just pretty basic, pretty straightforward. We've got a projectile that's fired from the ground level at an angle of 10 degrees to the horizontal. We need to figure out what is the minimum velocity necessary to ensure that this projectile will have a range of 100 feet. So, it's pretty clear, if you look at this just from a visual perspective, we're firing something, say, from the left side, and we know that this angle is 10 degrees. But based on how much force we shoot that particular object off with, that's going to have a direct impact on how far that thing is going to go. Even though we're shooting it off at that same angle, that initial force indeed does play quite a bit of a role here. And this could be something along the lines of maybe kind of wartime. Maybe we have infantrymen up in front of us that are like 100 feet away, and we want to make sure that our cannons that are behind them certainly don't bother them at all, and thus need to shoot beyond that 100-foot threshold. So first things first, let's get this thing started with a position equation, a position vector value function. With my students, I use the vector r of t. It's not really important what letter that you use. I know a lot of classrooms might use s of t for position. That's perfectly fine. But we need to remember that there is an I and a j component unit vector that we're going to employ with this. And we will first of all start off with the initial force in which we shoot this particular projectile with, and that's a force that we don't know. That is that velocity that we talked about. So I'm going to call that v in this case. And then we multiply that by t cosine of our angle measure in degrees, 10 degrees, and then all of this will make up our I component. Now, if that portion there bothers you, like I said, you might need to kind of go back and look at some other video that deals with using vectors to solve motion problems first, some of the more basic examples. All right, now we put together our vertical components, and to do this, we have kind of a similar situation. We still have that initial force V that we don't know, times the time multiplied by the sine of 10 degrees. But we also have to tack on our gravitational component of this particular expression. We're dealing with feet throughout the problem, so we're going to use -16 as my coefficient of t squared. And there actually is one other thing that I do need to throw into this mix, and that would be the initial height of that projectile from where we're firing it. But since it says we are firing it from ground level, I really would only be adding a 0 into this mix, which isn't going to change anything. So that will be our initial equation. Where do we go from here? Well, this is where I like the fact that this problem is really quite intuitive. It's pretty logical about what we want to do with this, I think. So if you think about this projectile, this cannonball, firing through the air and landing here at some spot that we hope to be 100 feet or more away, it probably makes sense that the vertical component, which I'm going to start with first, that would be the v times t times the sine of 10 degrees minus the 16t squared. If we fire this projectile and it lands right here where I've got it marked in the picture, the height above the ground, the vertical distance, is going to be 0, right? Because it just lands right on the ground. And you might look at that and think, well, what's that going to enable us to do? Because we have an equation that contains both a v and a t. Well, what we can do with this is actually solve it for that v. We could probably solve it for t or v, but it's going to be a little easier to do so for v because all we're going to do is add over a 16t squared, as you can see, and then I can divide by the rest of the terms that are sort of attached to the v, which in this case would be the t times the sine of 10 degrees. And in this particular instance, I'm going to go ahead and cancel those t's. Yeah, we run the risk that t is 0. Well, t is 0 only in one instance at the beginning, but we're kind of focusing more on what's happening when the ball, the projectile that is, reaches its destination, and that's going to be well beyond time being 0. So I have an expression for v, although in terms of t. Well, boy, you'd sure like to have another one of those, wouldn't you? Wouldn't it be nice to have an equation, a pair of equations with v's and t's in it? Well, we look no further than the I component. If we think about that I component, that would be namely the v times the t times the cosine of 10 degrees. By the time that this guy reaches its final destination, we would hope that he would be 100 feet away. Now, this problem really wants us to figure out this velocity that would send this projectile more than 100 feet, at least 100 feet or more away. So to make this a lot easier, let's just set this equal to 100. We don't need to use an inequality. Now, by setting this equal to 100, we can then parlay this into an equation that solves for v. So we would just simply divide 100 by t cosine of 10 degrees. Let's make this 100 look a little bit more like 100, huh? All right, so what do we do next? Well, we have a pair of equations that are both set equal to v. So why not we set those two expressions equivalent to each other? 16t over sine of 10 degrees set equal to 100 over t cosine of 10 degrees. Now we see that we could very likely cross multiply here to obtain 16t squared times the cosine of 10 degrees. And that would be equivalent, of course, to 100 sine of 10 degrees. And if we want to go ahead and solve this for our t, wouldn't be too tough to do. Initially, we'll just divide by 16 cosine 10 degrees. There we go, make that a cosine. And then, of course, we're going to have to end up taking the square root of both sides to finish this off. And as we do that, we also can be very conscious of the fact that our time, by just using basic logic, needs to be a positive number. I doubt that we're going to be able to shoot this projectile going back in time. So we won't worry about using the plus or minus of this particular result. So at this point, what I'm going to need to do is use a calculator to compute this particular expression, and I can go, let's go ahead and show you that here. I don't have that done previously, but it's not a big deal. I'm using the TI Inspire. Any kind of a scientific or graphing calculator will do the job here. So you have 100 times the sine of 10. Now you want to be really careful if you're using a calculator that is already set in radian mode, as you can see. You could change this to degree, but it's a lot easier in the case of the TI Inspire just to use this little button right here next to the G and just make sure we throw a degree symbol in there. Otherwise, we would have been computing this at the sine of 10 radians, which is a totally different answer. So we've got now at the bottom the cosine of 10 degrees. And by the way, the degree symbol can also be found with the pi button. And then quite often, you know, if we hit enter here, we might not be real pleased with what we get, because that's, you know, it's kind of hard to relate to a little bit. So I'll hit control enter to give me a decimal approximation. And 1.049, if you do round that, I guess you could call that 1.05. Trying to kind of stay consistent with the rules of rounding and take out 3 places here at least. So let's just call it that. Let's call this t approximately 1.05 seconds. Now, does that answer our question? Well, the big answer is no, it does not. We don't want to know when this projectile is going to reach that particular threshold of 100 feet. We've just figured that out. We want to know what velocity is going to cause this projectile to reach that particular threshold. So we got just a little bit more to do with this problem, and namely that is to go into a velocity equation and plug in our 1.05. Well, you've got 2 different velocity expressions with which to do that, and you got to think about, well, gosh, which one will we use? Well, I'll tell you what, I'm going to use the top one, then we'll kind of discuss the situation. And also, if I really want to be 100% meticulous about this, I probably ought to put an approximately there, because this is an approximate answer. We've already rounded, so we're never really going to be able to say that we've got the exact answer. So let's see, we've got 16 times 1.05. That would be divided by, I believe it is the sine of 10 degrees. All right, so let's go ahead and move to a calculator again and do that particular calculation. So we'll put in a fractional expression that consists of 16 multiplied by 1.05 divided by the sine of 10 degrees. Need that degree symbol again. Since I already have a decimal, as you can see here in my input, I'm pretty sure that I'm going to get only a decimal output, which is nice. 96 point, we'll call it 747 here, and I think that would be accurate enough. 96.747. We'll kind of go back and we'll interpret this in just a moment. But the question that I had earlier is, what if we would have used this version of V instead? What if we would have plugged this into the red expression? Well, let's take a look. So we would have 100 over 1.05 cosine of 10 degrees. Let's see if I can remember that, going to the calculator. We would have 100, let's get that fraction, there we got that fraction, 100 over, now remember that began with that value of t, and then we had cosine in the denominator. The answer? A little bit different, just a slight bit variation. Well, the reason for this variation is because of the fact that we did use a pretty liberal use of rounding of that time, 1.05 seconds. And probably as far as, say, you know, having a very good mentality in terms of, you know, advanced placement and their sort of line of thinking is that if we use more decimal places here, we probably will get a little bit better approximation. Now, I don't want to turn this video into a video that deals with the you know, rounding situation, but just really briefly, what if I were to copy? I'm going to hit Control V and I want to copy that particular expression. And if I were to like go back up into this guy here, and you know what, I think I may have 1.049. I tell you what, I'm going to type 1.04978. 4.978. We get a slightly varied answer there, which is honestly probably a better answer. Okay, what if the same thing were to happen here? What if we used a little bit better rounding and used 0.4978? You can see that our two answers are going to be a little bit more in agreement to 3 decimal places. I can't advocate enough the importance of ensuring that you can get a final answer that's going to be accurate to within 3 places. So my thought here, and the reason why I purposely did this problem so that I had this rounding error, is to reinforce that to my students and anybody else that's watching out there. That is awfully important. The better answer here undoubtedly would be 96.727. Now, usually I would offer a little bit of leeway on my free response type of questions, but this 1.05 was sort of precarious. Again, using the value of, what was it, 1.04978 is going to get you a little bit safer result here, 1.04978. So just think about that as you guys embark on some of your problem solving. Anyway, that takes care of it. That pretty much answers our question here. The minimum velocity that we need to fire this projectile would be 96.727. Boy, it'd be nice to get a label here. Well, it looks like we've got feet as one of our labels, and the fact that this -16 is already sort of attached to the gravitational constant of 32 feet per second. We definitely have feet per second as our label, and that would be that minimum velocity that we need. All right, anyhow, I hope this helps, and we'll see you next time.
Yo, VIP.